Hello, and thanks for your interest in our work called GEM, a generalizable ego vision multimodal world model that gives us fine-grained control over ego motion, object dynamics, and full scene composition. Before talking about the details, let's ground ourselves in why world models matter. Controllable world models let an agent understand its surroundings, predict plausible futures, and imagine alternative scenarios under user-defined constraints. Given that motivation, the obvious next question is, can a single model really cover all those what-ifs in the wild? Well, the answer is yes, because GEM can obey fine-grained controls on objects such as cars, pedestrians, and control the camera itself. It can generate accurate depth alongside the generated videos, and crucially, it generalizes across various cities, weather, time of the day, and other domains. Now, how does it do that? Let's look at the high-level overview. GEM is built on a diffusion video generation backbone, namely a stable video diffusion. Noise frames and depth latents are fed through a transformer unit. The latents of different modalities are concatenated, while the other control inputs are fed through either cross-attention or adding the feature maps to the output of the layers of the unit. Let's unpack those conditioning channels one by one. First, to control objects, we use a sparse set of dyno features representing different parts of the observations. This allows us to drag and drop objects to specified locations and times. This is how it looks like in practice. We extract the dyno features of the motorbike in green boxes and move them to the blue box in some time in the future. Then, the model does the magic of generating the desired motion. We can also insert objects by putting the dyno features. Or we could do a combination. Here we ask the white car in front of us to move to the right lane and also put a clone of it at the left lane. The second part are the skeleton controls, in which we render human joints, and this control gives us the power to depict a jaywalker or a hand wave. An example here is shown where we could either instruct the pedestrians to stop where they are or move in front of the car. Third is explicit camera trajectories, which let us enforce ego motions and are fed to the model through cross-attention. Here, given the reference frame, on the video on top, the model is given a right turning trajectory as control, and on the bottom, a left turning trajectory, which the model faithfully follows. Controlling short clips is great, but what about longer videos? GEM scales to long horizons thanks to a dynamic autoregressive noise schedule that strengthens a frame-to-frame causality and continually refreshes its reference context as we roll out into the future. Quality matters, so we benchmark with FIDM and FVD. Lower scores mean more coherent and realistic videos, and GEM consistently outperforms prior work across both metrics, as well as shows more stable long generations compared with the baseline. FID and FVD scores are not always accurate and are subject to some criticism. Therefore, we did a human evaluation study to compare GEM with Vista, our prior work. The subjects report similar quality of videos between GEM and Vista for short videos of 2.5 seconds, but constantly favored GEM's 15-second long videos. Of course, controllability isn't just visual. We measure how well instructions are obeyed. The evaluation shows high trajectory and object control accuracy, proving GEM doesn't just look good, but it also listens. To wrap up, GEM unifies multimodal control, long-range consistency, and a state-of-the-art visual fidelity in one model. We believe this is a step towards truly interactive video generation and closed-loop embodied AI. Thanks for your attention.